So I guess I'll start by thanking the organisers for setting us all up and for inviting me to talk, although you think by now they would know better. This is a progress report. Now, sometimes people say I have a progress report. I mean, they've done the work and they're not quite sure about the proofs, but we're not at that advanced stage. We've done some work. And so I'll try and make clear as we go on what's happening. And so it's worked with these four people, all of them are here. I remember once being at a conference where Rari was speaking and he insisted on inviting each of his co-authors to stand up so he could introduce them, but I will pass on that this time. Okay, so I'm talking about quantum walks, and I wanted to start from scratch. And there'll be no bras or kept hurt in the course of this talk. So what is a quantum walk? Well, you can think of it as a black box, but black boxes are boring. So today it's a pink box, okay? And you've got inputs and outputs, and I'll be explaining about that. Now the input, you can imagine someone sent you this kit, okay? You feed in a graph, and then you choose an initial state, and then you press a button, and it goes for a while, and eventually you get bored, and you press the stop button, and it spits out a vertex of the graph. Now, this is not a piece of hardware that's going to sell lots and lots of copies, but this is what it is. So you feed in and so once the graph is in there, you're going to leave how that's fixed. You're dealing with a quantum walk on that graph, okay? You choose an initial state, which will be a vertex of the graph, although more general things are possible. You wait a certain time, you press the button, and it feeds out a vertex of the graph. Now, it's slightly more complicated than that. If you repeat the process with the same initial state and the same time, you may not get the same result. So what you observe at that time is actually a probability density on the vertices of the graph. So at a given time, the probability you see the first vertex, second vertex, that's a probability density. So what we're discussing mathematically is it's a sequence of probability densities. Now, this is the same as a classical random walk on a graph. There's a sequence of probability densities. It's just the rule by which we're computing it is going to be more complicated and makes a big difference. And so the basic question you ask is, if I choose this initial state and wait this time, what is the probability that I observe at this particular? Once you have that, you have all the information that quantum physics can give you. There's nothing else that is missing. I mean, although this is not a trivial matter. Okay, so that's the very broad outline. So we need to, well, usually they say you should think outside the box, but today we're going to work inside the box. So what is actually going on internally? Well, I'm still going to be several steps away from anything real or physical. The initial vertex would be called a state. And a state is just a positive semi-definite matrix with trace 1. Now, if physicists may have to try, experimentalists may need to realize this thing, and so they may have a lot of problems, but we're just mathematicians. We just need to know it's a density matrix, the trace is 1, and it's semi-definite. Everything else is physicists' problems, and I'm thinking it's a mathematician. Okay? So the simplest example of a density matrix would be, well, this would be, if you want, normally written in brass kit. So just take EA is the standard basis vector indexed by the vertex A. And so this is a diagonal matrix with a 1 in the A position and 0 everywhere else. And that's certainly semi-definite, and it's certainly got trace 1. So that is an official state. Okay, so that's the state. Now, I said the graph's in there, but how is the graph interacting with the system? Well, the graph is giving us what the physicists call a Hamiltonian. And I noticed that when Alistair was asked what is a Hamiltonian, he very carefully avoided the question. And I'm going to follow in these footsteps. For our purposes, we can think of the adjacency matrix, the Laplacian, or the so-called unsigned Laplacian. So here I'm using delta to be the matrix of degrees. And if you can't tell my deltas from D's, you're going to have trouble, but we'll try. Okay, so these are possible, and these are representative. And the point is also they're given us by the physicists. It wasn't the graph theorist said, let's play with these particular things. So the first paper worked with the Laplacian, and then fairly early on they switched to using the adjacency matrix for no apparent reason, and nothing. I never seen any discussion as to why they changed. It makes very little difference to what happened, so that's probably the important thing. So there's the Hamiltonian. Now, the Hamiltonian controls the walk, and so your system is sort of in some sense changing the time, and so those changes are governed by this matrix U of t, which we construct in Hamiltonian. So it's just the exponential of ITH, and since H is symmetric in all cases, I'm talking about the U of t will be symmetric, but it's also unitary, which is important because it's representing a change of quantum state, and change in quantum state has to be unitary. So the point is a graph from the graph we can write down a number of possible Hamiltonians. I'm going to be using Laplacian as much as anything today, but it doesn't really matter. Laplacian, sinus, Laplacian, adjacency matrix. Compute U of t, and then the rule is that if you're given an initial state d at time d, then at time t, this is your initial state. This is another matrix that's similar to d. because it's matrix D, matrix inverse. It's got the same trace as D, so it's a density matrix, okay? And so I'm just denoting by D of T. So if D were your initial state, then D of T is what the state would be at time T. So, okay, so that's how the graph works, that's fine. And so we can, and so now our problem is, as I said, you know, the problem is to work out what probability when we press the stop button that we observe a particular vertex, how to get that out. Now, at this point, what we're doing in quantum terms is a measurement, okay? And I noticed David's skirting around that in his talk, so I'll follow that principle. How to get the output. The probability of observing the vertex B, given that you start at vertex A, is just the BB entry of that D sub A of T. D sub A of T is a density matrix. It's quasi-semi-definite, so the diagonal terms are non-negative. This trace is 1, so they sum to 1. So they form a probability distribution or density on the vertices. And so what about the off diagonals? It's actually worse than that. I'm not even really entitled to ask. If you need the off diagonals, you need to set things up a little differently. The jargon would be that we're measuring at a standard basis, and this is what people in quantum computing do. So there are choices as to how you measure. You measure at standard basis, and so you've got if I know what dA of T is, then I can write down the probabilities to just the diagonal entries. And so now I've got the walk completely specified. You tell me the initial density matrix. You tell me your Hamiltonian. I compute this and I have the walk. And as in some sense, you know, a dice with several $1 million of grant money gone into construction. You know, if your graph's got 6 vertices, you've got 6 outcomes. And it's just, you can ask questions at different times and you get different results even when you repeat it. Okay. So, and so I said we need to determine a probability density on the vertices of the graph, but that probability density is just the diagonal entries of your density matrix at the time you measure. Any questions at this point?
D sub B is just a single one.
Yeah. Now, there are a number of questions you can ask. You can do things about mixing. You can do things about quantum search. I'm going to focus on this, one of the older, simplest questions. The question is there a time T? If you start at vertex A, is there a time T at which the state is actually D sub B? At this point, your fancy device now functions like a perfect dice, except it always gives you the same answer. Okay, so the reason this is interesting because in context of quantum computing, if this happens, you can use this to insert to copy the state of a qubit. And basically, one of the theorems in quantum mechanics says you can't copy a qubit. There's no operation which will take 1 qubit and produce 2 copies of it. And so this gives you a way of sort of getting around that prohibition of the cost of waiting a bit of time. So, that's the question we're asking. Simply, we want to choose our initial. We choose our graph. We're going to have a graph. We're going to have a time. We're going to have an initial state D sub A, picking vertex A, and we want to ask him: is there a time in which the state is actually D sub B? And this is called perfect state transfer. Have I said anything too offensive yet, Alistair? So the other point is that I said, well, I took that my initial state being E sub A transpose, and well, E sub B transpose, but you've actually got a lot of choice, and I want to be exercising on this choice as we go on. So this is the first one I talked about, and this is what I'll call a vertex state. You could take it, instead of just taking exactly one non-zero entry on the diagonal, you could take a set of ones on the diagonal, and I'm calling it a subset state. Bill and these students have looked at what they call group state transfer, which didn't like this a bit. The other thing that matters and is significant is a so-called pure state. This just means a density matrix with rank 1. Okay, and so this is a pure state. This would not be unless your set's got size 1. I'll be talking about pair states. And so, well, I've written out, I wasn't kind, didn't write out the matrix to you. So it's just going to be half 1 minus 1 minus 1, 1. So it's the Laplacian of K2. And you throw the half in because the physicists want to have a trace 1. I may get sloppy about that as I go on, because most of the time what matters is the density matrix being quasi-semi-definite. You can always fix the scalars later on. And well, as I said, well, Qiuting Chen, for example, worked on this for a master's thesis, and there's a generalization just, well, why stop at Laplacians of edges? Okay, we can take Laplacians. So these are all valid states. The Laplacian's quasi-semi-definite. This scaling, so the trace is 1. So these are possible. My point simply here, there's a bunch of, well, some sense, interesting states, and interesting from a graph theorist point of view, maybe from a physicist point of view or not, that's another question. Okay, but they're graph, they're reasonable states. And there's just as much reason to work with this as there is to work with that, from a mathematical point of view. So, as I said, well, this is all well and good. But what I was threatening you with is I wanted the diagonal entries of that product. And it's all very well and good, but okay, your first step is I give you the adjacency matrix for argument's sake. Well, and then after you compute x by TA. Well, you don't want to do that. And then I'm going to do that similarity. So this doesn't look like a lot of fun. It's not quite as bad as it looks because we can use spectral decomposition. And so that's what comes next. My Hamiltonian, which, as I said, think adjacency matrix or Laplacian, can be written as a sum eigenvalues times projections. The eigenvalues are real because the requirement is the Hamiltonian has to be emission. And so the eigenvalues are real. And we have these projections onto the eigenspaces. And for all the cases we're considering, they will be real as well. And this will actually matter a bit at one point. Okay. So that's just the standard spectral decomposition of a emission matrix. Now, once you have that, you can immediately write down the formula for U of t, because it's x of ITA. And so you just apply your function, x of IT, to the eigenvalues of your matrix, and you get what's shown here. Okay, so we get, so here's an explicit formula for U of t. And so we can work with that. So the point is that the E sub R's, they're spectral idempotents for the original graph. So you can use standard linear algebra. We just grind away in Sage. We can get the spectral, and so we can get the spectral decomposition. So we can compute this. And so this is actually an efficient computational way of doing things, as well as being convenient to actually do calculations. Okay, and to prove results of that system. So it's got two advantages in that sense. So we can compute U of t, and so then we get a formula for D of t. So you do the work, you get this sum. Unfortunately, our sum over two variables, EDIT, difference of eigenvalues times these products. Projection, density, projection. Okay, and so if we have perfect state transfer from A to B, then you would just have this, all I've done is change that to D of B. So you get that sum. Now, on the first, it seems surprising you can get anything from that. I can't scroll that up, can I? But the key thing that's going on here is that in all the examples, and this is not just the examples I've been playing with, the examples that the physicists are normally using, both D sub A and D sub B are real. And these are the idempotents of a emission matrix. They're real as well. So the only thing there which is not obviously real is that x of B to the IT eigenvalue difference, which of course is not real in general, but everything else is real. But you can show that these terms here are linearly independent, with respect to the trace in a product, for example. Or you can multiply on the left by E sub k and on the right by E sub L, in which case you pull out one term on the right, which will be EDIT theta k minus theta L times EK dA EL. And over here you'd have EK dB EL. And so then you're telling you got something real equal to something times something real. That tells you that something must be real as well. Complex number of norm 1. So if it's real, it's plus or minus 1. Okay, and this is where the nice properties of perfect state transfer in terms of continuous walks on graphs come from. You don't need it. It's simply the fact that these things are real. Well, so as I said, the first consequence we get is, well, this is equal to plus or minus 1. Now, if I'm feeling lazy, I can replace t by 2t, and then I can get that E2IT eigenvalue difference is equal to 1. That's just easy to work with. That already tells me something. So that tells me that if this is true at time t, at time 2t, this is just 1. And then that right-hand sum there turns out just to be d sub a. So if I have transfer from A to B at time t, at time 2t, you get transfer from A back to itself. And so what I say is that vertex is periodic, or more generally that state is periodic. This is interesting from a number of points of view. One thing is that if you're actually trying to search for examples of graphs with perfect state transfer, periodicity is easy to work with. If you're trying to prove theorems, periodicity is easy to work with. So your first step is you find the periodic vertices, and then you check, so it's periodic at a certain time t, you look at what happens at half t. And so you see whether it's PSC or not. Okay, so, and we're getting all that just simply from the observation that states are real. There's a similar trick you can do when things are algebraic, which is useful in other contexts, but I won't be doing that today. So I mentioned periodic. The other point is, well, I don't think that's quite right what I've written there, but we won't fuss with it. if that should be an X, 2IT, let's fix that. E to 2IT, so 1. That tells me that the point is that 2IT eigenvalue difference is an integer multiple of pi. Okay, and so that's true for R and S. So let's pick a second pair of indices K and L. That's true. Same thing is equal to integer multiple of pi. And so from that you get what's called the ratio condition. That if you take the ratio, the difference of these two eigenvalues, that ratio is a rational number. Okay, now there's a few details I'm sort of sweeping under the rug here. I'm only really concerned about the eigenvalues where the pairs theta R and theta S such that E sub S is not zero. If they're zero, they just go away. And I'm basically going to ignore that question today. There's something coming up which I would refer to as eigenvalue support, but I plan not to fuss much about that today. This has a very important consequences because the eigenvalues of a graph, or graphs, of adjacency matrix or Laplacian, are algebraic integers. They're not nice algebraic integers. The adjacency matrix tend to be irreducible. Okay, so there's nothing very nice about them. And so the difference of two eigenvalues is just some nasty algebraic integer, it's not in general an integer. So there's something quite strong happening here. And the consequence of this is you can actually show, using Goa theory, that the eigenvalue difference are integral multiples of the square root of some integer, which might as well be square root. And so, or they could be integers. So they're in a certain sense, they're trying to be, they're either integers or quadratic integers. And so you've got a very strong handle on it. So that tells you that I got these eigenvalues theta R and theta S. The difference, if they're different, they differ by at least 1. They can't be too close together. And this is an important constraint. Come back to us. The other things we learn, which don't follow immediately from what I've written down, but probably do, but they're not going to go into it. If I do have vertex state transfer from vertex A to vertex B, then the induced subgraphs X drop A and X drop B are co-spectral. The adjacency matrices are similar. This is a combinatorial property, a combinatorial consequence of vertex state transfer. So this is kind of nice because you've got this physical property of vertex state transfer tying up to something which is quite familiar to people in graph spectral theory. Okay. The other thing is for the moment is a technical detail. The consequence of the condition is that these I'll do it here, that E sub R dB, E sub R is equal to the corresponding term for A. And if you look at the off-diagonal terms, they differ by sign. Now, there's a top line that's going to come back and bite you in the bum a bit, but the other one's not going to be so important. So I'm thinking here, the question is, I've got this vertex state transfer between two states. What does this tell me? And so I've got co-spectral vertices. I've got an integrality condition on the eigenvalues. I need to give you the next one. I need to bring another definition. It's what I call the average state. So I'm giving it a limit of it's a limit of d of t integrated from 0 to big T and then scaled by 1 over t. And just to throw some big words around, this appears in the literature as von Neumann's ergodic theorem. And it's always nice to be able to throw von Neumann's around when you're talking to physicists. It tends to keep them quiet. But the other point is, you can actually go in and do a little work and verify fairly quickly that average state is just equal to this. So this gives you a linear algebra definition of the average state. And remember on the previous last line here, if there's PSD from A to B, then these two things are equal. I'm moving the screen. And so if we have vertex state transfer from vertex A to vertex B, they have the same average state. Now, it may say, I don't know whether this helps or not. The density matrices are positively definite matrices. You're applying U of t bar U of minus t to them. So you're in some sense observing an orbit of a one parameter subgroup of the unitary group on the space of positively definite matrices. Okay, of trace 1. So that's a complex set. So you expect to be able to average things. Each orbit's got an average. And this deep hat is what the orbit is. And so for those of you who know, you can use essentially the same argument I've just given there to prove that if you actually get pretty good state transfer from A to B, average state is still equal. Same proof. And I'm going to say that two states are strongly co-spectral if their averages are equal. This is, in a sense, not the standard definition, but it's the most general definition, and it's one you're stuck with today. So I'll leave that. Again, any questions?
Yeah, I have a quick question. So you said you have an orbit of the unitary group on the space of positive semi-definite matrices. So unitary group is compact, right? So this thing,
Yeah.
so this one parameter subgroup has got to sort of either be periodic or converge or something. What's going on when you say it's an orbit on the positive semi-definite matrix?
I've got a group acting on a set.
Uh-huh.
Actually, I've got a one parameter group acting on a set. So I have what I really have is a homomorphism from the reals into the group. That gives me a sequence of group elements. And that's giving me, I'm looking at the image of my starting point under each of those elements, and that's giving me an orbit.
Okay.
And I'm saying that what you're seeing there is actually an average over that. So you can think of this geometrically.
Uh-huh.
I've never found this helps my students, but you can think of it geometrically because you need to think in terms of total groups. But or you can just go, I mean, you prove that this equal to this just by using the formula I gave for D of t with the E dit theta r minus theta s and average, and the off diagonal terms go to 0, and so you get that. So you don't need any theory. You only need linear algebra and basic calculus to get from here to here. So the point about cospectral, well, I'll come back to this in a minute, but if you want examples of graphs with cospectral vertices, well, you pick your favorite strongly regular graph, and you pick two vertices, they're guaranteed to be strongly cospectral, and you can pick your strongly regular graph to have no automorphisms of the identity. Any two vertices are still strongly cospectral. Any two vertices are still cospectral. So it's easy to give examples of things that are strongly cospectral. But the disappointment is for strongly regular graphs, those vertices are not strongly cospectral. Okay, and so you don't get PST between vertices on a strongly regular graph. But anyway, you know what? Say just define seminar rooms with no clocks, but that's not my problem, is it? The next comment is okay. So perfect state transfer, I'll try to convince you is interesting, and I muttered something about cloning states, and so it's possibly even useful. The bad news is that it's rare. So this is something I proved many years ago. If we work with the adjacency matrix, there's only finitely many connected graphs with maximum bonus decay where you get perfect state transfer between two vertices. So there's only finitely many connected cubic graphs with perfect state transfer. Okay. So, you know, good news or bad news, that's the news it is. So there are lots of examples. I mean, the hypercube gives you examples of perfect state transfer. I mean, you can get infinitely many examples in various ways. But, well, for example, if you take a Cuddy graph for Z2 to the D, most of those Cuddy graphs admit perfect state transfer, which is something Sophia pointed out to me. So that's the story there. So that's something for, I mean, talking about vertex state transfer, but I did threaten you with these other states earlier. And so what if we decide to use some other, one of our other choices of Hamiltonians, for example, the Laplacian? Now, in fact, the same proof still works. And what's even worse is when you start looking at the example, trying to find examples of graphs with perfect state transfer between vertices relative to the Laplacian, there are even fewer. I don't know why. And I don't think anybody else does either. So they're scarcer. And so I was thinking about this, and I thought, well, you know, if we're using Laplacians and thinking about Laplacians, some reason occurred to me it might be natural to think about, instead of using the vertex state, to use what I was calling the pair state, Laplacian of edge. The question is, I'm going to use Laplacian to give me my Hamiltonian, which is not a big change, it makes no real difference. And I'm going to use the pair state in place of the vertex state. So I'm going to ask questions about transfer between this pair of vertices and this pair of vertices. Now, so naturally we thought about the case as Tina was working on this for a math thesis. And I guess I can say the title of her math thesis was edge state transfer, but the paper we wrote in support based on this is called pair state transfer for reasons to become clear in a little while. But so we take two pairs of vertex, we're using Laplace, and we ask, can we get transfer from one to the other? Now, the first thing is experimentally, yes, it works a lot better. I don't have an explanation for this, but I just pretend I'm a physicist moment, say experimentally it's okay. So that's, you know, but it'd be nice to have a better explanation. And so, okay, so I think the next slide is just giving me the definition of pair state. I should have thought of that. So there it is. And so we get ideas to think about transfer between pair states. Now, the summary is, as I said, it's much easier to find examples, and I don't know why. The other thing was related to the remark I made about the titles. This graph here we can take the pair 1, 6 and pair 2, 5. That gives me 2 pairs. I get 2 pair states. On that graph, you do get transfer at time pi and 2 between the first pair state to the second pair state. Something a little weird is happening. Well, when you think about it, there was nothing that ever said that it had to be edges. And at some point it occurred to us to ask this question, and Tina produced this example quite quickly. And so there it is. So that's fine. So what's happening? Well, it is what it is. Now we'll go a little further. Let's just go on. Where's that? I stop early. So we can ask this question, and this only occurred to me a night or two ago. And the proof that I have for the earlier result saying that perfect state transfer was rare does not apply in this case. And so this is an open question. I suspect that the answer is yes, but as I said, the proof I have doesn't work. And it makes it interesting because, okay, so to prove that, you're going to come up with some new techniques, and I'd like to see those. So the vertex state transfer using the Laplacian that my earlier result applies. And if I'm doing pair state transfer using the unsigned Laplacian, I'm okay. But in this one case, with pair states on Laplacian, I don't know what happens. So that's an open question. So, okay, so this talk, as I said, is something to progress report. I indicated that there wasn't much progress as there might normally be the case. So what's been happening is, well, we have a weekly meeting on Thursdays, and Ada comes down from Toronto, and afterwards we've been sitting around discussing some of these things. And the thought occurred to me as well, we're looking at pair straits, and I remember seeing a paper by Simone Severini and someone else who's now forgotten, where they were looking at Laplacians as states, because the Laplacians are possibly semi-definite matrix. And so, the question is, well, why stop at pairs? Okay, so we can take two graphs, y1 and y2, take the Laplacians, scale them if we're going to be fussy. Well, actually, I do want to scale them now, and then consider transfer of one to the other. Now, in this context, my Hamiltonian is going to be the Laplacian. You're actually free to use other things. I don't know what happens, but it seems natural when you're using Laplacian states to use Laplacian Hamiltonian, but that's the full strength, strongest reason I have for doing that. And so this is the setup. Now, as I said, the point is that we have some information which I'm about to give you, but basically we have lots of questions. And normally with this sort of, approaching these sorts of problems, we do a fair bit of computation and then base our discussion based on what we find in that computation. But we haven't done the computations yet in any detail for reasons that will become clear as I go on. So, well, the first thing, like Dave was saying this morning, it's nice to start with an example. So I probably copied this down correctly, but there are two graphs on 3 vertices there, 1, 2, and 3, and 2, 3, and 4. And in this case, you get Laplacian transfer from one of those subgraphs on 3 vertices to the other at time pi on 2. Generally speaking, if you get perfect state transfer between 2 states, it's going to happen to be by time 2 pi, unless you're being really contrived with your Hamiltonian in your states. And I think I've got that picture right, but it's gone through several people copying it out by hand. And so maybe the best thing is let's go on and don't embarrass ourselves. So I can work out so if I start with a graph y1 and I'm going to y2, then this is the standard formula, and I get the same sum before. And so the meanings of the ERs have changed a bit. These are now projections on the eigenspaces of the Laplacian, but what the hell? So we get that formula. And as before, this is all real, and this is real. And so the point is, the argument I was giving you about real states doesn't just apply to vertices. All I need is reality. Or anybody needs reality. And so that tells us again, I'm going to get that if there's transfer, then e to it theta r minus theta s is plus or minus 1, and they'll get various conditions of that type. Now, whether I get I'll still get integrality conditions so long as my Hamiltonian is rational. If you start getting crazy, then I can't help you. But if you use a rational Hamiltonian, and all Hamiltonians I've shown you are rational, and I haven't seen it apart from a few things that come up in search algorithms. Generally, the states people use are rational, so I'm not making an arbitrary assumption. The first thing we're learning is, okay, that the two graphs y1 and y2, or the adjacency matrices are similar. because UT is giving me a similarity transformation. And in fact, something stronger is true. You can take the Laplacian y1 plus any scalar times Lx, or Laplacian y2 and the same scalar times x. Those two things are similar. Now, this is going to be quite strong because there's no reason for why this matrix has to commute with that. If they commute, of course, I get that for free, but they don't have to commute. I mean, we don't have enough way examples yet to be really convincing, but the point, and in fact, stronger things are true. I mean, why stop with that? I can take polynomials in y1, L of y1, and polynomials of L of x, and they will all line up. And then your next step is, oh, we'll take the algebra generated by these things. Now, unfortunately, the algebra is not necessarily a good invariant because what tends to happen is the algebra you get will be the full matrix algebra of all n by n matrices. So you can't just ask in terms of the algebra, you've got to ask a more refined question. But the point is, there's a very strong similarity condition coming up. Now, this is all right if you're just using, if y1 and y2 are vertices, there's no particular problem, or edges, but it's clear that as y1 and y2 get larger, this condition is going to get stronger and stronger. And so where that leads us is something that's clear to me at this point. And the other thing about this is that what's happening is, leaving aside any physical motivation at the moment, now I'm getting myself a bunch of questions, spectral questions about Laplacians of graphs and subgraphs. And these questions seem quite interesting in their own right. But the reason we got to them is because we're thinking of these questions in physics. Now, I started my career doing graph spectral with Ivan Gutmann in mathematical chemistry. And one thing I learned from that is that questions which come up, here we come up with a question. I don't know whether actually trying to talk mathematics with a chemist, physics is complicated enough, but doing with a chemist is really something else. But here we come up with questions, and I'd ask for the motivation. I'd say, well, maybe I don't need to know the motivation. What was the question again? And they turned out to be good questions because they were interesting in this other context and they're interesting mathematically. And the same thing's happening here. Okay. And so what this is giving me is now I've got relations, various relations on subgraphs of the Laplacians. Okay, and so these questions may possibly be interesting physics, I don't know, but I certainly feel they're interesting in mathematics. So if you're after transfer, because of our sort of general approach, we know that if we have transfer, we get periodicity, and so we can simplify our task by looking for periodic subsets rather than perfect state transfer. Now, once we have periodic things, we look for perfect state transfer. Now, there's a computational problem here. Is that okay? For the interesting cases, we're going to want subgraphs of 3 or 4 or 6 vertices. And suddenly I'm saying, well, let's go through the graphs on 12 vertices, choose all the 6 vertex subsets and see which ones are periodic. And there's billions of graphs on 12 vertices. Even on 9 vertices, there's 250,000. If you go through the 4 vertex subsets, you've got something like 40 million things to test. So I decided, well, I was saying at lunchtime, somebody, by the converse of Gordon Royal's, one of my favorite quotes, just from Gordon Royal, he says that sometimes several days feverish hacking can save you an hour's careful thought. And I'm taking the point here that I'll apply the careful thought first, and then we'll do the hacking. So there's this is why I'm saying this is a progress report, because we haven't done this. What I would call anything like a thorough investigation, what happens numerically yet, computationally. So leaving that aside, the point is that we can check reasonably efficiently whether a subset is periodic. Okay, we do that for a living, really, in other problems. Okay, so testing periodicity is not a problem. It's just going to be this. Fine, thanks. That's perfect. Thanks. So we can test that. We haven't done it yet, and that's why I said this is a progress report. Another context which I want to bring up quickly is, well, I was talking about various states, but I didn't give you a complete list. This theorem here is telling me if I have a graph with just one component with more than one vertex. So I'm thinking of a subgraph. It's simplest to think of a subgraph of my graph X, but it's got one non-trivial component, everything else is isolated. Okay, and I can write down a Laplacian state. If that's periodic, then so is this state. Well, this is not a state because I haven't normalized it, forgive me. And so the point is this, and so, well, it can be simple to test whether this state is periodic. And it's somewhat surprising, you can pull out other states of periodic. There's more than just the Laplacian itself. And I'll leave that at that. And I'll do that. Now, one thing about this is that we were thinking about, just announced a couple of results. Since we're thinking about when subgraphs are co-spectral, I had examples before, we started thinking about this a bit more, a few more general cases. one thing Xiaohong and I proved, if you have a strong irregular graph and you have two edges, E and F, a strong irregular graph, and you delete those edges one in turn, you get a pair of graphs. That pair of graphs, they're co-spectral with respect to the adjacency matrix. They're co-spectral with respect to the Laplacian, and they're co-spectral with respect to the unsigned Laplacian, all at the same time. And I don't recall seeing examples of that before. And if you pick your favorite asymmetric strong irregular graph on 25 vertices, you get 150 pairs of graphs, each of which are co-spectral in all three senses. Okay. And now we wouldn't have been asking these questions if we hadn't been thinking about the state transfer problems. And the other issue, well, this started with me giving a seminar. And as I said, if we have a Laplacian transfer between Y1 and Y2, then these two things are similar. And I more or less said, and surely that implies that Y1 and Y2 have the same number of vertices. Nobody looked very convinced, and we thought about it for a while. And the answer is it's not true. They don't have the same number of vertices. And here's a couple of pairs of examples. So what's happening is you've got these adjacent, so the scaled Laplacian of Y2 is similar to Laplacian of Y1. Now, this is a relation I've never seen anywhere. I have no reason to expect it to be true. It could happen on the adjacency matrix for all I know, I don't know. But we have examples that Xiaohong dug out on the Laplacian.
Great, thanks. Questions for Chris?
Yeah. So when you had Y1 and Y2 as subgraphs of X on this previous slide, and you had this gamma, is that scalar gamma? So L of Y1 plus gamma L of X is similar.
You choose gamma.
Yeah, my question is whether gamma is real or complex. Because did you need reality?
It doesn't matter.
Oh, you didn't need reality there. Okay.
I mean, as I said, much stronger statement to true because I could replace the products of those things would be equal as well. So there's one. But yeah, but gamma is arbitrary.
Okay, thanks.
Else.
So when you look at the Laplacian transfer, you've got a couple of examples there. Is it the case that when you put the initial state on, so when you put the initial state on, is it the case that the support is much smaller compared to number of vertices on the whole graph?
Well, it is in the example we looked at so far. And because of that spectral stuff, I'm thinking it's going to be very difficult to get large subgraphs. Because not only is the Y1 co-spectral with the Y2 in some sense, but the X minus Y1 and X minus Y2 are also co-spectral. Okay, so there's a lot of stuff going on, and that condition with the gammas that Bill was just asking about is also very powerful. So it's not going to be very easy, I think. We did the obvious thing and we looked at strong irregular graphs. Unfortunately, we can prove that well, vertices, edges, and triangles and strong irregular graphs, well, I say we was one thing, but we proved that in those cases, those states were never strongly co-spectral. So I can't get examples from strong irregular graphs.
Yeah, I mean, maybe this is like a silly question, but you know, as we started building up the from the single points to the pairs to the higher sets, just kind of made me think. I wonder if there's anything interesting to be said about like simplicial complexes and what happens when you have higher order higher order Laplacians. In particular, graphs that could then yield a simplicial complex of maybe higher order Laplacians to get extra information.
I think my response to this, I'm having quite enough trouble dealing with the Laplacians themselves. Yeah, that would be the long and short of it. And the other thing is, I'm vaguely constrained by the physics to some extent. I like to think of things which I could got to convince Alistair to at least listen to me seriously when I talk about. But yeah, I mean, there are a lot. I mean, this is the thing. You look at these things, you're getting questions, and they may have nothing to do with the physics. Doesn't mean they're bad questions, but I don't know.
So there's a scheme called shift firing on graphs. Is that in any way related to your work?
Shift firing on graphs.
It's not related to this.
It's not related to this. Okay, just wondering. Thank you.
Anyone else? All right, well, let's thank Chris again.